In the previous two videos talking about some applications or problem solving which needs the concept of ordinary generating functions, we had actually an exact value for that, but this time we had a more general item. In this time we have here for the number of ways to select 2n balls. We don't know how many are they, just represented by 2n, from n identical blue balls, n identical red balls, and n identical white balls. And this time, let's try to find out a formula that would stand, or general form that would stand for the question, which patterns on the a sub r for x to the power of r selections. That would mean we're going to look for the formula for a sub r following the concept that we should all get here the target of x to the power of r. So what would this be? It would be actually the formula for, or the coefficient for x to the power of 2n, because we're distributing 2n number of balls for these situations from these different perspectives. Now, let's look into this. Now, the use of ordinary generating functions here, we're going to try come up with a general form for the ordinary generating functions for each of the situation. Take note that this actually look like the number of integral solutions, just like in this form in the previous examples, the integral form, where x sub 1, the number of ways to select from. This will be our blue, okay? This will be the blue, this will be our red, and this will be our white. In short, we're going to add the number of blue, red, and white. That will give us the result of 2n. Okay, but this time we don't know the restriction. We don't know the value for blue, r, and w, but we know the restriction that there are only n. There are only n identical blue balls. In short, the restriction for b, for r, and for w would be just the value of them. Okay, for b, r, and w must be between 0 and n, because n is the maximum number of blue, red, and white balls, and there is also instances where they cannot be chosen. Okay, so for this, how do we write its equivalent ordinary generating function? For the number of blue balls, the restriction would be n. So you have here 1. It may not be chosen. X plus x squared plus x cubed, but it will end into x to the power of n, regardless of what that value is. We're going to end into that. This is also true for the number of red and the number of white balls, because they have the same restriction. So there are 3 sets of this form, and that means we can actually try to come up with one expression for the product of their ordinary generating functions, which is actually equal to, you will have here 1, that's 1, plus x squared, plus x cubed, until you reach here x to the power of n, and there are actually 3 pieces of them. Okay, so hopefully this is clear, because this is a process of finding a certain function that will describe us this form later on. And of course, our goal later is to come up with a simpler form of this. We know that n here is considered to be an example of finite until n. Okay? Because there's no condition that n is infinity. Until n. We just don't know what that n is. But if you're going to write this is actually an equivalent example of finite geometric series, where you can see that there is a common ratio from term to term, and that's actually x. And the formula for the sum of n, okay, geometric series, is 1 minus r to the power of n over 1 minus r, or r to the power of n minus 1 over r minus 1. So what's need to be done next is actually to simplify that in this form. So that is actually equivalent to 1 minus x to the power of how many terms are there? Is it just equal to n? Take note, we have here n is here, but we still have one more here. So 1, 2, 3, 4, 5. That's actually n plus 1 terms, because this portion here stands for x to the power of n, and we still have one more here for the non-selection. So that's n plus 1 terms, not just n, but n plus 1 selection. So n plus 1 over 1 minus x, and this is actually raised to 3. Now let's try to simplify this, and let's find out if we could actually come up with x to the power of 2n in the same process. This is actually equal to, by power law, 1 minus x to the power of n plus 1, that's cube, okay, and then over 1 minus x, and then you have cube, which can be written as 1 minus x power of n plus 1 cube sorry for that, can be written like this one here. Okay, you have 1 minus x power of n plus 1 cube, and you have here 1 minus x to the negative 3. Okay, which this is actually equivalent to this form, 1 minus x to the power of negative n. Okay, this is equivalent to the expansion of 1 plus n minus 1 combination 1 for x, plus 2 plus n minus 1 combination 2 for x squared. And for the nth term, you have r plus n, rth term rather, n minus 1 combination r for your x to the power of r. But so that we will not be confused with what do we mean by n, because earlier n was represented by the number of balls, and actually here the n here stands for the exponent of this expression. In this case, n is equal to 3. That would mean for the rth term, okay, for the rth term, it's actually r plus 3 minus 1 combination r. Okay, that's for the pair of x to the power of r for this expression here. And why are we using here the rth term? Because we would like to target x to the power of 2n, where this would be our r later on. And again, this is not similar to the n expressed here. So that is why we will attack here for the rth term. Okay, so this is in the form of 1 minus x to the power of n plus 1 cube. And for the rth term, we'll be using this form, r plus 3 minus 1 combination r x to the power of r. Why are we using this? Because all the terms in this expansion is actually expressed in this form. So for the rth term, in the same expansion, where our r later on will be used again to solve for this, and the coefficient for our target, we'll be using the rth term here. Now allow me to continue this by, of course, expanding this side, sorry for that, this side here, using the cube of a binomial using special product. So this would be equal to the cube of 1 is 1, then plus 3, the cube of 1, the square of 1 rather, times the second term. Okay, so pardon with me here, then plus 3 times 1 times the square of the second term. Okay, and then finally you have here plus the cube of the third term. This will still be multiplied. Let me erase this portion here. This will still be multiplied to this rth term. You will have here r plus n minus 1 combination r x to the power of r. Simplified form is actually 1. You have here minus now 3 x to the power of n plus 1. And then take note of this. What will happen to that? When you have that form, it's actually power of a power. So you just simply add multiplying the exponents, which will give us 2n plus 2, right? So that's actually here, this of course positive now, plus 3 x to the power of 2n plus 2. And you have here, that's cube of negative is negative. And similarly, n plus 1 times 3 for the power law is 3n plus 3. X to the power of 3n plus 3. Still we multiplied, let me arrange that, x to the power of r in this component, r plus 3 minus 1 combination r, depending on what would be our r later on. Distributing that here, you'll have the form x to the power of r minus 3 x to the power of n plus 1. Using multiplication law, simply add the exponents. So you have r here plus that, so n plus 1 plus r. Similarly, 3 x to the power of 2n plus 2 plus r, and minus x to the power of 3n plus 3 plus r. All of this will be multiplied to your r plus 3 minus 1 combination r. Since I don't have much space here, let me copy this portion and move it to another page so that we can actually add some scribbles here. Okay, hopefully that's going back. Hopefully this is clear why the expressions are expressed in this manner, because of the use of rth term, the cube of a binomial, and when we multiply numbers or expression with the same base, we add exponents. So again, we are now at this portion here. Let me paste the previous one. Okay, let me remove this scribble here and proceed. Now, how do we proceed to this? Take note again, our goal is x to the power of 2n, sorry, the x to the power of 2n. So let's try to multiply this to all of the terms. You have x to the power of r times r plus 3 minus 1 combination r, then minus 3 x to the power of n plus 1 plus r, then you have your r plus 3 minus 1 combination r, plus 3 x to the power of 2n plus 2 plus r. You have r plus 3 minus 1 combination r, and you have minus x to the power of 3n plus 3 plus r, You have r plus 3 minus 1 combination r. Take note, we want x to the power of 2n. Hence, for all of this to be considered, each of these terms must be equal to x to the power of 2n. And with that, the r values will be changed depending on what would be the r for each of those specific terms. Let me do it like this. For the first one, for this to be x to the power of 2n, our r should be 2n itself. This would mean the r here and r at the bottom should also be equal to 2n. Hence, you have here 2n plus 3 minus 1 combination 2n. For the second term, it doesn't work 2n here. We have 3x to the power of 2n. It doesn't mean that our r is also 2n. That is because when can this be exponent be equal to 2n? So in here, side note, n plus 1 plus r is equal to 2n. What would be our r? Transposing that, r is equal to n minus 1. Okay, because you have 2n minus n is n, then minus 1. So in short, our r for the second term is not 2n, but it's r minus 1. So here, you have n minus 1 plus 3 minus 1. And your r here is n minus 1, right? The third term, for this to be 2n, x to the power of 2n, what would be the value of our r? So you have 2n plus 2 plus r is equal to 2n. Our r, moving that there, our r is actually negative 2 because 2n minus 2n is 0, so minus 2. So you will have here, that's actually equal to, our r is negative 2 plus 3 minus 1, combination negative 2. Again, we'd probably have some items to consider here, but let's try to continue first. So you have x to the power, for this to be equal to 2n, so 3n plus 3 plus 1 must be 2n. Solve for r, that's actually minus n minus 3. Okay, so you have here negative n minus 3 plus 3 minus 1, negative n minus 3 here. Yeah, it's negative n because you remove it like that. Now, here comes some of the things that we need to consider. Of course, if our r for any combinatorial notation is negative, mathematical, that's equal to 0. Same as this, that's equal to 0. So we are left with the first two terms now. Let me change the color to blue. This will be equal to x to the power of 2n. And then you have 2n plus 2 combination 2n minus 3 to the power of 2, 3 times x to the power of 2n times this one here. You will have, that's n plus 1, right? N plus 1 combination n minus 1. Okay, that's negative 1 plus 3 plus 1. Okay, for this now, factoring this out because that's our target, you will have here 2n plus 2 combination 2n minus 3. You will have here x times n plus 1 combination n minus 1. This would be x to the power of 2n. This is now the coefficient of x to the power of 2n. This tells us the number of ways to distribute 2n balls with the condition earlier. And this is now the general form for our a sub 2n. Say a sub 2n and the answer to the intended problem. Okay, so we use all of this to get that, including the items here on the previous page. So the answer again, if I'm correct to write here, let me just copy for the purpose of this. So you have, okay, copy that. So here, this would be our answer. So it's actually in blue. Let me rewrite that using another color, let's say red. So you have here 2n plus 2 combination 2n minus 3 times n plus 1 combination n minus 1. This is the number of ways to select 2n balls from n identical blue balls, n identical red balls, and n identical white balls. But there are also some concerns here because take note of this. We have n minus 1, and what if our n is actually 0? So this would become 0 minus 1, so we're going to cancel that one. So there is also another form for this. Let me go back to the previous page. I mean this one page here. Okay. There are also some notations. So for example, 2n plus 2 combination 2n. Okay. And you have here n plus 1 combination n minus 1. We know that there are some identities that we have learned before, such as this 5 combination 3 is equal to 5 combination 2. Okay? That is because they will have the same result. Now, if we're going to look into this perspective, actually you will have here 5 combination 5 minus 2, right? And you have here 5 combination 5 minus 3. That means the values in these regions here are just a process of removing such values from our n here. That's why you look at this one. These two are just equivalent, because when you subtract 2 from 5, that's 3. When you subtract 3 from 5, that's 2. So just like this one here. So what is my point? My point here is this. How do we make this simplified form? Because if n is equal to something else together with this, and they must go hand in hand, how should it look like? Now take note that our 5 here, let me just look at 5 combination 3, is actually equal to 3 plus 2 combination 3, right? That means, looking into this one, we have the same value here, same as this as well. So we can just simply use this other value, as this is also equivalent to 5 combination 2. So this, it would be the value here at the bottom. So for this time, instead of 2n plus 2 combination 2n, using this is also equivalent to 2n plus 2 combination 2. So the factor, or the addends, okay, the addends, okay, earlier is a combination 3, so they have that, but this could also be taken here, and they're equal to one another. Similar thing for this here. If we're going to write n plus 1, okay, as a combination where n minus 1 is present, it's actually equal to n is equal to actually n plus 2 minus 1, right? Or you have your n minus 1 and you have here plus 2. Okay? Because we're going to use this one to substitute that here, so we can use this second. In short, this will be also equivalent to n plus 1 combination 2. Okay? Again, this will be using the portions, or when you break the addends, n plus 1 is just equal to that, rearranging them to match with the denominator, or the r, sorry for that, not the denominator, and you have here plus 2. This together with this earlier can be used for that, and then we have the same r here, so you have minus 3, and this is a better form than the other one, because if n is actually 0, it would actually be a fault on our item considered. So in short, the previous one here could also be written as this final form, okay, 2n plus 2 combination 2 minus 3 times n plus 1 combination 2. Let me go back here. N plus 1 combination 2. Alright? So this is now the answer. Better, because our r's here are actually expressed as constant aside from this. But they are actually have the same concern, but this is just problematic if n is equal to 0. Thank you very much for watching.